right, well, go ahead and take your homework out if you would, please. We just went over the quiz in here. As I told my students in here, a large portion of the test will be very similar to that quiz that you just took. So lots of different types of equations on this test upcoming. But for now, I want to look at the homework, which there was a word problem handout, and then on the back side, I'd asked you to do page 128, number 39. So let's start in your textbooks. Page 128, number 39. And you were supposed to solve a quartic equation, n to the fourth, positive 5n cubed, positive 5n squared, negative 5n, negative 6 equals 0. And what do we do first in solving one of these higher power equations that really there's no good way to factor this? Kendall, Kendall, what do we do? Good, the P over Q, where P, remember, class, represents all the factors of the constant, and then Q represents all the factors of the leading coefficient. Well, the good news is the leading coefficient is just a 1. So really it's the factors of the 6, the 1, 2, 3, or 6, of course, positive, negative on all of those. And of course, I would start by testing the 1. Did the 1 work, Kendall? Yeah, 1 plus 5 plus 5 minus 6 does in fact equal 0. So wait, we got lucky on the first try. We're going to take this root. By the way, what would the factor be, class? X minus 1, or n rather, minus 1 would be a factor, but the positive 1 root we're going to put next to our list of coefficients and use synthetic division, where we'll bring down the 1, and then what two steps alternate, Michael?
Say what now?
What are we going to do?
I blanked out. Hold on.
We bring down the 1, and then what do we do?
Oh, you multiply.
Multiply to get 1, and then we
add
to get
6.
Then we multiply to get
6.
Then we add to get
11.
And then we multiply to get
11.
And we add to get
6.
And then we multiply to get
6.
And then we add to get
0.
And it better be a 0. Now, I'm going to take all of this and turn it into a polynomial. What is the polynomial here, Genesis?
1 n cubed, positive 6 n squared, positive 11n, positive 6 equals 0.
There we go. And by the way, I can see here that continuing to test positives doesn't do me any good, right? So again, if you can see that, it'll save you time. Negative 1 I'm willing to try, but if it doesn't work, I'm not trying to positive 2, because that'll make everything positive, and a bunch of positives never adds up to 0. So let's plug this negative 1 in here to get, Genesis?
Negative 1, positive 6, negative 11, positive 6.
And does that add up to a 0? Man, we just keep getting all the breaks here. All right, so we'll put the negative 1, which is our next root, meaning n plus 1 is our factor, next to the 1 plus 6 plus 11 plus 6, and we'll do synthetic division again, because this isn't quadratic. We need to get it down to a quadratic. Bring down the 1, Maddie, and then to get? Add to get? Then?
Multiply to get negative 5, and then add to get positive 6, multiply to get negative 6, and so get 0.
There we go. And of course we can plug these in here to get the n squared, positive 5n, positive 6. Now, Audrey.
You can backwards FOIL.
Good, backwards FOIL. You could use the quadratic formula. This FOILs really easily into
n plus 2, n plus 3.
and so I get 2 more roots. These are my first 2 factors here, the n negative 1, the n positive 1, now an n positive 2, and an n positive 3. But what are my roots going to be?
Negative 2, negative 3.
Good, along with the negative 1, and then the original root we found, which was the positive 1. How many got all 4 of these roots? All right, now this is longer than what you would need to be able to do on the test. Obviously, it was longer than what you had on the quiz, but you understand the process and how, again, if we had to start with the 5th power, we'd end up doing not 2 synthetic divisions, but 3, right? The higher the power, the more synthetic divisions you have to do. Once you finally get it down to a quadratic, we're done from there. Technically, you could even do this on the quadratic, but why? Quicker to do it that way. Questions? All right. Let's take a look at the word problem handout. So look back to the other side if you had worked the equation on the back side. Hold up the handout, by the way, so I can see that it is completed. Good. All right, excellent. Let's go ahead and take a look at the first problem here. Brandon says a school spent $61 before tax on 6 dozen sodas and 8 dozen cookies for a reception. If a dozen sodas cost $2 more than a dozen cookies, find the cost of each. How many unknowns do we have?
2.
And they are?
Cookies and soda.
Cookies and sodas. Now, not individual cookies, but cookies by the dozen, sodas by the dozen as well. So a dozen sodas, a dozen cookies, but I'm lazy, so like you, I'll just say soda and cookie. All right, and it tells us the total amount spent, but it also tells us the total number of sodas and cookies. The number of sodas and cookies is not unknown. It tells me how many sodas?
6.
6 dozen. Of course, these are by the dozen, so I don't need to say 72, okay? Because it even describes the price in terms of the dozen. And then cookies, it just seems weird not to have an S at the end. How many dozen cookies? 8 dozen cookies. All right, so the number of each is not what's unknown. The unknown comes in the price of each. And which of these gets to be X, Abby?
The cookies.
The dozen cookies. Because it says that a dozen sodas costs
$2 more.
So we would represent the dozen sodas.
X plus 2.
All right, a lot of times when we've worked these, we've had the X values in the number and the prices have been clear cut. Here, for only the second time, the number has the given value. The price has the unknown. How many got the steps started off correctly? All right, questions on this? Okay. Well, your saving grace is it'll actually work out the same because as long as you did the next step correct, to get the total money spent just on sodas, again, 6 dozen sodas at X plus $2 a piece, how much total money is that, Genesis?
6x plus 12.
And 8 dozen cookies at X dollars a dozen. And so this is all the money spent on sodas. This is all the money spent on cookies. And if we take all that money and add it all up, it comes to what, according to the problem? Genesis?
61.
So my equation should be what?
14x plus 12 equals 61.
There we go. How many had that equation? The 14x plus 12 equals the 61. All right, then to solve, we'll subtract the 12 to get anyone. 49. And that doesn't divide evenly by 14, but if you work it out as a decimal, it comes out to a pretty easy number.
3.5.
Yeah, it comes out easily to 3.5, but since X represents money, I'm not going to say 3.5, but rather, class, $3.50. And then the sodas were $2 a dozen more than that, so sodas would have been, class, $5.50. And it asked for the cost of each, and there we go, $3.50 for a dozen cookies, $5.50 for a dozen sodas. How many got those answers? All right, so all the way through to completion. Question?
I had the cookies, but for some reason I had $7 for the sodas.
Did you do X plus 2 or 2X?
X plus 2.
So maybe your brain just went 2X. For some reason, brain doubled instead of adding 2 to 350 to get 550.
I guess so.
All right, and then Genesis, you kind of walked me through the last step, so it seems like you're good to go now as well.
Yes.
All right, any questions at all on these types of word problems? All right, the other type of word problems that we've been working on lately, besides the number of each, price of each, total money for each, was the ages. And go and take a look at this one. Have Sarah 8 years younger than her brother Lee. 5 years ago, Lee was 3 times older than Sarah. How old is each now? And that should be a question mark at the end, not a period. Who writes these? The unknowns here, Audrey.
Sarah and Lee.
I'm sorry?
Sarah and Lee.
Sarah and Lee. And who gets to be X?
Lee.
Lee, and Sarah would be
X minus 8.
X minus 8. And that's their ages right now. And that comes from the first sentence. But then we're going to time travel. We're going to go, class, into the past. 5 years ago. What's true of everyone 5 years ago, class?
5 years younger.
5 years younger, right? True of Sarah and Lee as well. How would I show that in the past, 5 years ago, Sarah was 5 years younger, Matt?
X negative 13.
And then for Lee, X negative 5. You knew what my next question was going to be. So once we've taken care of the 5 years ago, those 3 words are this column. That's what gets us here, those 3 words. And after we've gotten this column, the rest of the sentence finishes the equation. It says Lee was 3 times as old as Sarah. How do we represent Lee, class? X negative 5, says right there. How do we represent was? How do we represent 3 times as old? 3 times something. How do I say Sarah? X minus 13. And there we go. Lee, past Lee, we've time traveled, remember, was 3 times as old as Sarah. Again, the past Sarah. How many have that equation? X negative 5 equals 3 times the x negative 13. Okay, questions on that? Get your now, do the time travel, and based on the time travel, set up your equation. Tell you what, at your seats, and several of you did not get that, go and solve that very quickly. You may want to go back to some previous lessons and re-watch maybe some of those word problems. Again, it's the upside of being in 2021, almost into 2022, where you can actually go back and re-watch past lessons we've done. Previous to this year, you could never do that. Get that extra practice. And what do we end up getting for x, class?
17.
17. So that's how old Lee is right now. Which means right now Sarah, class, would be 9. But 5 years ago, how old was Sarah? Good, Maddie. How old was Lee 5 years ago, class? Was he 3 times as old? Yeah, but as the question states, should say ask, how old is each now? There's the answers we're looking for, 9 and 17, their ages. Questions on this? All right, again, there's a number of these word problems that we did. All you got to do, pretty much the start of every lesson, for several lessons in a row, so go back, maybe, see this is lesson 77. My guess would be somewhere on lesson 70 is where you'll see those. And if you start the lesson and the screen is on the screen, then there you go. Get a chance to practice with them. And if you don't see it, then that lesson we didn't do word problems. So we pretty much started lessons that way, if you want that extra practice. All right. Let's talk about the test, which will be in our next lesson. Test tomorrow, lesson 78. Sections that you'll need to be ready for. First of all, section 2.5. You might want to jot this down. Section 2.5 was imaginary and complex numbers. Imaginary and complex numbers. How do we know that a number is imaginary, class? What are imaginary numbers in general? Square roots of negatives. Make sure you know that. A square root of a negative is imaginary. And what's the key to working with imaginary numbers? Pull out your eye. First, before you try to do anything else with the number, get the eye out of there. You know which is, you got a cup below your eye. Anyway, somebody trying to take it too literal. So anyway, imaginary numbers, pull out your eye. Now, what is a complex number, Michael?
It is a number that is imaginary and real.
Good. Part of it's imaginary, part of it's real. Like, for instance, negative 5, negative 3i. Well, part of it's real, negative 5. Part of it's imaginary, the negative 3i. And we said that in order to add imaginary numbers or complex numbers, really simply, you just add it up. Like, what would I get if I added these two numbers together, Kendall?
2 positive 2.
2 positive 2i, right? You just add the reals together, add the imaginaries together. We remember that? Now, if we were subtracting, we know Genesis, we never really subtract in algebra. We add the inverse. So when it says subtract, I'm going to change this to adding, and then both the real and imaginary would change, right? This would become negative, that would become negative. And now when I add my complex numbers, I get
Negative 12. Negative 8i.
there we go, negative 12, negative 8i. Would end up being our answer. Any questions on subtracting complex numbers? All right, multiplying complex numbers. Let me change back to the positives that we had. If we multiply two complex numbers, how did I say we would do that, anyone? I heard it, I think. FOIL, right? They're similar binomials. So first, class, Negative 35. Outer. Negative 25i. Inner. Negative 25i, negative 21i. And then we multiply the last together. But it's important to remember, of all the fundamental powers of I we talked about, I squared came up the most. We need to remember I squared is simply a negative 1. And so negative 15 I squared really just becomes positive 15. And now this real negative 35 and the real positive 15 combine, class, to give us negative 20. And then the negative 46i is just there. Technically, the outer and inner combined for that. Here, the first and last end are combined. And we would get this. Questions on that? We also divided. And of course, we said that normally, when we have division, we don't show it with this symbol. How do we normally show division, Abby?
Fraction.
Right, so the negative 5, negative 3i would normally be over the 7, positive 5i, something like that. And to divide by a complex number, because the I represents what, class? Square root of negative 1, right? That's what I is. I is the square root of negative 1. So since this is a radical value, we have a 2-term radical denominator. What do we do to get the I out of the bottom? We multiply by the conjugate, remember. To divide the complex numbers, multiply by the conjugate of the denominator, which would be what here, Kendall?
7 negative 5i.
It's 7 negative 5i. By the way, if this were a negative 7, this would stay negative, right? It's only the middle sign that changes. But so let's say 7 negative 5i, and then 7 negative 5i here as well. Of course, the reason for the conjugate is so it creates what special case, class? Sum and difference, which square the first, square the last, put a minus sign between them. Square the first, class? 49. Square the last? 25i squared. And of course, we put a... But again, the I squared is really negative 1. So that means this is really a positive 25. So really the denominator, class, comes to a 74. Then in the numerator, we just have to do what? FOIL. And Maddie, we multiply our first. The outer inner gives us what, anyone? Positive 4i. That wasn't on purpose. And then the last gives us what, anyone? Positive 15i squared, but we know that's going to really become negative 15, which can combine with the negative 35. And of course, we still have the positive 4i here. And now, I don't actually mind a negative first term because real has to come before imaginary. But there is something I should do to this complex number. Negative 50 plus 4i over 74. Again, I'm sorry? Yeah, I can take a 2 out of everything. What will it reduce to if I take out the 2, Brandon?
Negative 25, positive 2i, and 32. No, yeah.
And there would be our answer. I knew what you meant. All right, questions on these? All right, are there any of these you say, ooh, I'd really like to practice those processes again? Could we do one of those on our own? Go on, once we all feel confident on complex numbers. All right, again, it seems like ages ago. I mean, obviously, Thanksgiving break doesn't exactly help how ages ago it feels, but throwing that whole week off in the middle, but that's big. Kind of building on this in section 2.5, we also worked quadratic equations, which are really, they were on the last test, right? But quadratic equations had never worked out to imaginary or complex answers before. So we took a look at those. We also looked at rational equations, section 2.6, where we could potentially have, again, imaginary or complex roots. Also in section 2.6, we were working with rational equations that turned into quadratics. So remember something like 2 over a 3x minus 15 is equal to, say, an x negative 3 over, say, an x squared negative 2x negative 15. Something, say, like that. Again, it's rational, but it's also quadratic, or it would at least become quadratic. And of course, this is a special rational equation class. This is called a proportion. How do we solve proportions?
Cross multiply.
Yeah, we can cross multiply. And of course, when we cross multiply the extremes here, anyone?
2x squared.
All right, piecing the answers together. I'm hearing from around the class. Again, just distributing a 2, right? And then here, when we cross multiply the means.
3x squared. Negative 24x.
Good.
Positive 4.
All right. And of course, since it's a quadratic, since it's a complete quadratic class, we want to set it equal to 0. And I'm going to put the 0 on the left side because the bigger x squared is over here. When we bring everything over, Michael, what does it become?
Negative x. Oh, we're doing it that side. Okay, x squared.
Because I don't like first term negatives.
Yeah. Negative 20x.
Good, because you're adding the positive 4x.
Positive 75.
There we go. And of course, we can backwards FOIL x and x, negative, negative. 75.
20.
Or should we complete the square? We could. That was supposed to be that hard. 15 and 5. There we go. Genesis to the rescue. I was this close to completing the square. And so we ended with 2 possible answers here, class. 5 and 15. But remember with the rational equations, the denominators couldn't equal 0. Well, here, what number would give me a 0, class? 5. So x can't be a 5. Here, if you were to factor x negative, let's make that x positive 3, x negative 5. Again, x can't be 5, x can't be negative 3, though that wasn't one of the answers I got anyway. And there would be my only answer, 15. Anyone remember the shortcut I told you could possibly use? Though, again, I'd be careful with using it, but shortcuts we could use on a proportion like this. Yeah, if we factored at the get-go, it seems almost counterintuitive because you're making more work for yourself in a way. And I said there's 2 times you can cancel factors. If they're both in the denominators, which we could have done that, or if they're in the same fraction with each other, you could cancel them, that's just reducing, but never cancel something out of both of the numerators. And so that could have saved us a little bit of time, still would have got the same answer of 15. Questions on these? Do you remember the rational equations? It's been a little while since we've worked those as well. Questions? Again, that was section 2.6. By the way, real quick before I get too far along here, at your seats, go ahead and work this problem. It's just a basic quadratic, but one where answers will come out complex or imaginary. All right, once we get to this point, we see we can't factor it. We only have 2 options, class. We could complete the square, or we could use the formula. I think completing the square is easiest, but remember, you've got to ditch the constant term. So the 11's got to move out as a And what do you put in its place? What goes in the blanks, class? 4. How do you get the number? 2 steps, class. You half and square. What do we do? Half gives me 2, squared gives me 4. I'm going to put that on both sides. Again, that's the b over 2, and you square it. So that this PST becomes squared, all equal to, and then we've got to take the square root of both sides. Look at the x negative 2 equals positive negative, pull out your I, leave the square to 7, and then to finish it, we just add the 2. Technically, before the imaginary, so real comes first, and then imaginary. Had we opted to go with the formula, we would have said A is a 1, B is a negative 4, C is the 11, while it's in the proper quadratic form, and then negative B plus or minus the square root of B squared minus 4AC all over 2A, where 16 negative 44 would give us negative 28, where I could factor that. I could pull out the I, and then I could go 4 times 7. So I could say 4 plus or minus, out of the 4, pull out a 2 times the I, leave the square of the 7 all over 2, divide by 2 gives us 2, divide by 2 gives us positive negative I squared 7. Same answer. Either way we work it. Questions on that? Again, that was since the last test. That seems like ages ago because it was about 4.5 weeks ago, it feels like. But that's the way it goes. 2.7, radical equations. Radical equations. What are my 2 key steps, class? Anytime I see a radical in the equation, isolate the radical, square both sides. Again?
Isolate the radical, square both sides.
Still kind of weak. All right, so if I had the square root of 3x positive 1 minus 5 is equal to 2, I'd isolate the radical and square both sides. Isolate the radical means I do what here, Genesis? Add 5 to get 7. And then when I square both sides, it's going to give me what?
3x plus 1 equals 49.
All right, struggling to get it out there. And then to finish it out here, let's go to Audrey.
Subtract the 1, 3x equals 48, just 16.
There we go. Do I need to check it? If there's only one radical, you can really get away with not checking it. Remember, if there's multiple radicals or there's variables in the radical and variables outside, you do definitely need to check. But if only one radical, yeah, don't really need to bother. But something like this, write this down, the square root of x squared negative 11 minus 4 equals x negative 5. Well, here you see variable in the radical, variable outside the radical. Here, you're going to have to worry about maybe getting an extraneous root. At your seats, give you a moment to work this on your own. And it checks. How many got the x equals 6 for your answer? All right, questions. Add the 4, makes it an x negative 1. Square both sides. Don't forget, square the first, square the last, multiply and double. If you don't multiply and double, it says that negative 11 equals 1, which is a lie. No solution contradiction. But when you multiply and double, obviously we go from there. Questions? Now, if there's 2 radicals in the same equation, for instance, we have the square root of 2x plus the square root of 2x minus 3, all equal to 1. Here's another time where we are going to have to check and see if we might have an extraneous root in our answer. But when there's 2 radicals, when we say isolate the radical, I mean isolate the biggest radical, then square both sides. So we would want to do what to isolate the biggest radical, Brandon?
Subtract the square root of 2x.
Right, move this little guy over and get the square root of 2x negative 3 all equal to 1 minus the square root of 2x. So we isolate the biggest radical, and then, class, we square both sides. Obviously, when we square on the left, that's easy, Brandon. That's just... But on the right side, again, when you're squaring, just like here, when we square, we're squaring a binomial. Square the first, square the last, multiply and double. So over here, Maddie, we square the first. We square the last.
Negative 2 times the square root of 2x.
Well, that's multiply and double, but great job with that. And then we square the last.
Positive 2x.
There we go. All right, so we square the first one, we square the last, again, positive 2x, and then multiply and double. 1 times 1 is 1, double is 2. Don't forget the negative and the square of the 2x. Questions on that part? And unfortunately, we still have a radical. So what do we do now, class? Isolate the radical, right? We just cancel the 2x's away. We could even move the, maybe double switch here, get 2 square root of 2x is equal to 4, then divide away the 2, so the square root of 2x is equal to 2. So isolate that radical now, and then once again, square both sides to get, so x is equal to 2. And, but again, always want to check. Here we checked, right? Because there was a variable inside, variable outside, right? Here there's multiple radicals we want to check. And we plug in the 2's. And thoughts? No. Square root of 4 is 2. Square root of 1 is 1. 2 plus 1 does not equal 1. So here, class, there is no solution. I will tell you on a test, if there's no solution, that's what would go in the blank. But I better see the extraneous root at the end of the word. Does that make sense? You're not going to get the credit for no solution unless I can see what the extraneous root was. My suggestion would be finish the problems, then go back and check, since there won't be that many extraneous roots. There'll probably be at least one somewhere on the test. But questions on this? All right, that was section 2.7, radical equations. Sections 3.1 to 3.3 were on the quiz we just took, which we've already gone over. You've got, for instance, from that quiz, we had fractional exponents, which, again, this is just a fancy way of showing roots. We had binomials, or polynomials in general, raised to fractional exponents. We had the equations that weren't in quadratic form. We had higher power that were in quadratic form still. And of all the things on the quiz, the only one I got a request for was to work one of the problems where it had fractional exponents in it. Let's take a look at that very quickly. So if I had, let's say, x to the 1/2 minus, check that, x minus x to the 1/2 equals 72. Something like this. Where we got a fractional exponent. And of course, the other one doesn't really have a fractional exponent. But remember, my suggestion was always get a common denominator. How could I rewrite a 1 so it has a common denominator with the 1/2? 2 over 2. And so now we've got this common denominator, and it's kind of in quadratic-y form, isn't it, right? We got to double this power, and then it's gone. So we should set it equal to 0. Bring the 72 over as a negative, and then backwards FOIL. How do I split up x to the 2/2 here, Genesis?
And 1/2.
Good, x to the 1/2, x to the 1/2. Of course, the sign tells me
Different.
one's positive, one's negative. How to split up a 72? 9 and 8. All right, so we would want which one to be which to get the negative one right here?
8 and 9.
8 the positive, and then 9 the negative, okay? And then what do we need to do? Back to Genesis. Good, set them both equal to 0. So then we end up with x to the 1/2 is equal to, move the 8 over, and x to the 1/2 is equal to positive 9. And then how do I get just plain old x? How do I get rid of that 1/2 power? Well, technically that's what 1/2 power means, isn't it? That just means the square root of x. So really we would want to I've isolated the radical in a sense, so then we could square both sides, right? Now, writing it this way with the 1/2 power, you're just going to raise to the reciprocal power. This is a 1/2. If we raise to the 2/1 or just 2, and that would get us our answer here, right? X. So x here is equal to, we square the -8, and when we square the 9, but again, this is a radical equation. Even though it didn't look like a radical equation, it is one. So if there's a possibility, class, for extraneous roots, which root do I already think is extraneous? I've got my suspicions about 64 because I had to square a negative. Well, here, remember, this was just x. We wrote it as x to the 2, so it was just x. So that's 64. And then what is 64 to the 1/2 power, the square root of 64? -8 minus 72 is equal to 0. And I kind of suspected that here. 81 minus, what's 81 to the 1/2? 9, the square root. Minus 72 equals 0. Yes, so this one's extraneous. This one checks. But again, it's just the reciprocal power. So this next one's probably going to be very obnoxious. So this is for illustration purposes only. But if I had, x to the 4/5 minus 2x to the 2/5 plus, I don't know, 6 or minus 63 equals 0, for instance. All right, well here, we would factor class the x to the 4/5 into positive, negative, 7 and 9. There we go. So we end up with an x to the 2/5 equals -7, x to the 2/5 equals 9. What power do I raise to Genesis to knock out a 2/5? Well, if I raise to the 5th, it still leaves me with an x squared. 5/2. There we go. And what I do to one side, of course, got to do to the other. And here, if you did this on your calculator, it would say no solution. Square root of a -7, class? Yeah, it's going to be imaginary, isn't it? And then we're going to have to raise that to the 5th power, but imaginary to the 5th power is still imaginary, so that really gives you no real solution, at least. There are imaginary solutions, to be sure. And then here, we raise this to the 5/2 power. Well, again, what are the square roots, remember, of 9? Positive and -3. Again, even denominator, don't forget the positive, negative. So positive, -3, then end up getting raised to the 5th power to get what 2 possible answers, real answers. How about 243 and -243 is what we memorized. 3 to the 5th was equal to. Questions on that? That actually worked out okay. I was like, oh, these numbers are going to be awful. It wasn't so bad. Questions? All right. We've gone over word problems. Again, my encouragement is go back. If you're struggling or feel nervous about those word problems, don't just be like, well, I guess I'm doomed tomorrow. No, you can go back on YouTube and find the portions you need. The quiz you just took, kind of use that as a reference. Make sure you're up to speed on those. Rational equations / proportions. The P over Q. Did anyone want to practice any more P over Q? We've got just a couple minutes. We can do one problem like that. And need to see another one? Or are we good on P over Q? Everybody in here feels good on P over Q. Sorry, YouTube. All right. Last questions for the test tomorrow. Again, test covers sections 2.5 to 3.3. No written homework. Your only homework is do whatever you have to do to be ready for the test in our next lesson, lesson 78. All right. Well, have a wonderful rest of your day. When the bell rings, you will be dismissed.